Hello again. This is Math 2270 coming to you from the College of DuPage. And the title of this lecture is Final Exam Content Guidance and Take-Home Problem Statements for spring of 2022. Copies of this PowerPoint slide are in your syllabus tab for your additional reference. As always, be an attentive learner while watching this video. So your final exam will consist of 15 equally weighted problems drawn from the following topical outline. There will be one problem dealing with infinite series solutions of ordinary differential equations. There will be three problems dealing with the Laplace transforms, including Volterra integral differential equations, Dirac delta functions, and Heaviside step functions, and these could be initial value problems. There will be three problems dealing with systems of differential equations, including non-homogeneous system initial value problems. And there will be five problems stemming from, and this question mark really is, I don't know exactly where we broke off the first half or not, but there will be five problems in this section, and I think this may have been the first half, including potentially Cauchy-Euler equations, Bernoulli equations, Clairaut equations, separable equations, first order linear equations, exact equations, second order non-homogeneous equations, and it could involve the annihilator or variation of parameters approach, and some word problem modeling problems. And then there are three problems that will be take-home problems. There will be one of them involving numerical solutions. This includes the Euler method, the improved Euler or Hahn technique, three-term Taylor series, and then the fourth order Runge-Kutta equations. So they're numerical solutions. They're also qualitative solutions. That's the second one. And the third one is a modeling problem. And these will be due in Blackboard. I need to create a place for you to upload them, and I expect this to be a legible and single PDF addressing all of those. Some students have turned these in to the math desk at the Learning Commons, and that I suppose could work too, but the testing center will not accept these. Okay, so here is problem number one. Consider the following very nonlinear initial value problem. So you have dy dt is t squared minus y squared sine of y, and y of 0 equal minus 1. So you're to use each of the following techniques with a step size of h equal 0.5 to approximate the value of y of 0.4. Students should not round off between stages, keeping all the digits available in the default mode of Excel or whatever program you're doing this in, the interest of accuracy. But in your final answer below, so each step in the table to 4 digits after the decimal point accuracy. So 4 digits accuracy like I'm showing you here on those. I do expect you to completely fill out the table. Number two, use a direction fields program, and you could use WinPlot or some other program of your choosing to plot the direction fields associated with this differential equation. That's the same one that you had in number one, the nonlinear one. Use the utility, whichever one you use, to show the particular solution for a dozen different initial conditions, including the one in problem one, the initial condition. Do a screen capture and paste it here of the results, and give me a narrative where you comment qualitatively on the long-term behavior of these solutions. Use complete sentences in your narrative. Finally, number three, this is the modeling problem, and I think you should be able to do this. Assume a coordinate system where the origin is the point where the supply pack is released. The positive x direction is the direction the plane is flying, and the positive y direction points downward. Assume the horizontal and vertical components of the air resistance are proportional to the square of the velocities. This actually changes the problem significantly from some of the ones that we have done. Part A, Develop a system of differential equations and initial conditions to model the system for x of t and y of t. Clearly state any additional assumptions in your write-up. Part B, using the appropriate model, and as engineers, using accuracy to the nearest foot, round off only at the end of the problem, determine the horizontal distance the pack travels, assuming the plane's altitude is 1,000 feet above the ground, the plane's speed is constant at 300 miles per hour, the proportionality constant for air resistance is K is equal to 0.053 in the correct units, and that the pack weighs 256 pounds. And here's a little picture that may help you with your work. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself, because self-care is important, and of each other, because we're all in this together. May God bless you all.